Good afternoon, everyone. So my name is Peter Schmitt, for those of you who don't know me. I'm going to attempt to cover a dissertation in about 35 minutes. So we'll see how successful I am at that. But this is essentially an overview of my dissertation. It's been a long yet rewarding journey, right, Mick, to get to this point. But we are galloping towards the finish line here. My graduate committee has a copy of my dissertation that they're currently reviewing, and the final exam is scheduled for April 4th. So it's fast approaching, right? So this is, again, this is an overview of that dissertation. The title is The Characterization, Assessment, and Shear Strength of Turfgrass Soil in North American Thoroughbred Racing. Okay, so brief overview. You're welcome to stop me, by the way, if you have questions. That's totally fine. I'm obviously going to try to leave as much room as I can at the end, but if you feel compelled to stop me, that's totally fine. It's not going to offend me at all. Overview, so obviously some introduction material. The second chapter of the dissertation is currently published in the Journal of ASABE. It's titled Laser Diffraction Analysis of North American Turfgrass Horse Racing Surfaces. The third chapter is currently published in Animals, Comparison of Devices for Race Day Characterization of North American Turfgrass Thoroughbred Racing Surfaces. The fourth chapter is obviously prepared within the dissertation. The intent is to submit to sports engineering shortly after defense, titled Effects of Natural and Synthetic Fibers in Turfgrass Horse Racing Surfaces as Characterized by Triaxial Shear Test. And then obviously some concluding thoughts. All right, so introduction. Catastrophic injuries to racehorses are obviously a particular concern for the racing industry. That's defined as death or euthanasia of the horse within 72 hours of the race. That's obviously according to the Jockey Club. Catastrophic injuries are tracked by the Equine Injury Database, also part of the Jockey Club. When it comes to the riders, there is not a comprehensive injury tracking system similar to that with racehorses, but minimizing catastrophic injuries to racehorses, we know that protects the riders. There's research out there. This paper that I'm quoting here was Peter Hitchens was the lead author. So jockeys were found to be 171 times more likely to be injured when they rode a horse that died during a race. That makes sense, right? So the more we can keep the horse upright, we keep the jockey on his back, and everyone goes home at the end of the day. The causes of catastrophic injuries are multifactorial. There's a lot of reasons why a horse could go down. The racing surface is one that affects all horses in competition. So it's obviously the one that people on this call pay the most attention to. The OBST, which I'll get into in a minute, or on a biomechanical surface tester, is sort of the primary device for assessing a racing surface. There aren't firm limits as to acceptance criteria for the OBST, and instead we focus mainly on minimizing spatial and temporal variation. As a result of all the events that have sort of led to changes in horse racing, here in the United States, there was federal legislation that established the Horse Racing Integrity and Safety Authority. That governs many aspects of racing, one of which is, of course, a racing surface monitoring and maintenance program. When it comes to preparing a surface, we know that the ideal surface will allow a small amount of slide during the primary impact phase of the gait, and then should support the hoof as it applies horizontal shear loads for propulsion. Shear failure is kind of one of the things that we're paying the most attention to with this dissertation. We know, so the ability of the surface to be able to withstand those shear loads will definitely affect horse performance, potential risk of injury, and it also creates divoting, which in turfgrass is a unique concern as compared to dirt or synthetic, because obviously that's a tearing of the turfgrass plant from the surface, leaves a non-uniform surface for the athletes to follow, and it also reduces the plant's ability to regenerate its root structure. Racing in North America is historically conducted on dirt, on ovals, and on counterclockwise directions, which is kind of a one of the unique things here in North America. But turf has been gaining in popularity. 11.5% of all starts in 2009 were on turf. And in 2022, that grew to 17%. So what do we know that we can sort of bring into this dissertation? Obviously, soil particle size distribution has a big effect on the mechanical properties of a surface. By that, we're largely focused on infiltration rates and shear strength. Particle size distribution is traditionally characterized by sedimentation methods. That's problematic for racing for several reasons, which I'll get into. I'll leave that one until I get into the first research paper. The OBST, I should have spelled that out, Orano Biomechanical Surface Tester. I'll have to make a note of that. This is the primary device for assessing a racing surface, and it's recognized with an ASTM standard. It replicates the point of the horse's gait where the highest vertical and shear loads are applied. It's the gold standard for pre-race meet inspections, seasonal inspection of the racing surface. There are some constraints, mainly complexity, size, and of course, disturbance of the racing surface that limit its use for daily applications. Again, we'll get into that one when we go to the second research paper. We also know that fiber reinforcement has been shown to increase shear strength of soils without inhibiting drainage. There's a lot of papers on synthetic fibers. Synthetic is normally polypropylene, not always. There are many different types of soil reinforcement. There are some papers on natural fibers as well. A range of applications from terra mechanics, geotechnical engineering to playing fields for human sports, and not a lot as it focuses on equine sports. Arguably, the number one thing that we're concerned about with this dissertation is the ability to continue to hold racing on turf surfaces during or directly following inclement weather. So this requires a free draining profile that can move as much water as possible vertically through the profile, with the shear strength to support a thoroughbred at a gallop. And obviously, those surfaces have to consider the ability to cultivate turf grasses. So the first paper on laser diffraction, as I said, mechanical properties of a racing surface greatly dependent on soil composition. That is traditionally determined by sieve and sedimentation methods, either hydrometer or sieve pipette. Those are reported on a mass basis. It's based on Stokes' law, which assumes spherical particles suspended in solution. That is an assumption that we now know is not, let's just say it's not 100% accurate, particularly for clay particles, which resemble more pancakes than they do spheres. Sedimentation methods also require large samples, around 100 grams. Removing this much material from an active turf track is a problem. So that's one of probably the biggest thing that we're trying to minimize with this research. And as many of the folks in the RSTL room there can attest to, sieve hydrometer is fairly labor intensive. Just to collect the hydrometer measurement takes at least a day. Laser diffraction is what we were looking at to mitigate a lot of these concerns. Requires much smaller samples on the order of about 1 gram. From this research paper, the smallest samples we used were 1/4 gram, and I think the largest were around 1.5 grams or 2, I can't recall. So these samples can be collected from aeration cores, which are a part of normal maintenance. So that's a tremendous benefit for racing, because we don't have to do any extra disturbance of the racing surface. Results for laser diffractions have already been shown to be repeatable in other soil science research, has a greatly reduced cycle time, around 15 minutes, as opposed to a day for hydrometer. And one major difference of laser diffraction as opposed to sedimentation methods is that it, obviously, like Lexi was just saying, it works on the scattering of light, and so therefore it reports on a volume basis as opposed to a mass basis. So as a result of the volume basis measurement, there are potential concerns over treatment of organic matter in soils. I'll get to that throughout this The purpose of the study, there were two hypotheses that we were looking to investigate with laser diffraction. The first of which was that we could characterize a racing surface with as few as 8 samples. And the second was that there would be different archetypes of racing surfaces. That was something that we kind of brought into this research. We knew that there were different archetypes of dirt surfaces from Christy Mahaffey's paper. We also documented the turf grasses grown, the climate factors, and the mineralogy for each racetrack. So we started by collected 96 samples from Keeneland. So that was a high resolution sampling that we used to evaluate the first hypothesis of whether or not we could use 8 samples to characterize a track. Why did we choose Keeneland? That's a common question. Keeneland was chosen because technically it should be one of the more difficult racetracks to characterize with a small amount of samples. Keeneland was originally constructed / renovated in the mid 1980s, and it's received, 40 years worth now of regular maintenance. It's had several, let's just say, cosmetic surgery along the way. It's been widened. It's been, had some nips and tucks along the way, especially around the outside. And we know that there are still outside along the outside rails, some parts of that race course are still native soil. So 96 samples were collected from Keeneland, and then we collected 8 samples from standard locations at 22 other racetracks across North America. That was used for the second hypothesis. All of those samples were submitted to laser diffraction, of course. Organic content was left in the samples. There is not great agreement among existing research as far as should you leave organic content in or should you remove it prior to laser diffraction. We elected to leave organic content in for the purposes of this research paper. We did 3 replicate measurements per location to ensure that we were getting repeatable results. We also determined organic content separately using loss on ignition, and mineralogy, was determined by X-ray diffraction. And then statistical analysis. So organic matter and the particles greater than 2 millimeters were compared with a simple linear model. And then a repeated measures ANOVA was used to evaluate each of the particle size classes, like Lexi was showing just a minute ago, measured by laser diffraction. We used the repeated measures ANOVA because we had 3 replicate measurements per location. And we also looked at the percentage of variation that 96 samples show, the percentage of variation that 8 samples could have characterized out of the 96. I hope that makes sense. I hope I'm saying that right. Hypothesis 2, tracks were grouped into archetypes based on observation. So you can make a fairly good guess just by looking at them, but obviously that was not the final say. So similar to above, organic and particles greater than 2 millimeters, a simple linear model with ANOVA, repeated measures ANOVA for each of the particle size classes from laser diffraction. And we also did a principal component analysis to investigate the variation between surfaces. Overall results. So did a total of 816 laser diffraction measurements. Spent a lot of time with the exerciser. So there it is. Sample size ranged from 1/4 gram to 2.5 grams. So you do have to vary sample size in order to achieve the manufacturer's 10 to 20% obscuration requirement, depending upon the composition. So, and different materials have different sample size requirements to achieve that obscuration value. Weighted residuals range from 0.1 to 0.8. Those are all well within the manufacturer recommendations. Average organic content was about 5.5% by mass, and the range was about 1.3 to 17.5. So that's a pretty big range of organic content across the 23 different racetracks. Mineralogy was predominantly quartz, feldspar, and plagioclase. hypothesis one. So there was no significant difference in mean values observed in 8 samples versus 96 samples for all particle size classes measured. So every bucket, every group of particle size classes, the mean values were statistically the same between 8 and 96. So yes, 8 samples can characterize the mean values of a racetrack is what we concluded there. As far as the variation is concerned, depending on the particle size class you're looking at, the 8 samples were able to see somewhere between 6.5 to 80% of the variation that 96 samples shown. That's, like I said, not a great shock when you factor into, the running lanes are significantly different from the outside rail, and we knew that going in, but now we have, we know the limitations of this sampling method, I guess, is what I would say to that. For the second hypothesis, laser diffraction was able to detect significant differences in mean values among the archetypes. So there's the principal component analysis plot is in the backup slides. The repeated measures ANOVA evaluated each particle size class measured by laser diffraction. And so there was ultimately 3 archetypes. The first one was an engineered surface with fiber. So that is essentially a bespoke high sand content surface with a synthetic fiber reinforcement. The second one we called engineered without fiber. Again, that is a custom surface that retains more fine content in lieu of fibers. That's their method of increasing shear strength, but that is at the cost of drainage. And then the last archetype was a native soils. So there were 3 out of the 23 that still had native soils. Laser diffraction. So results show that we were getting quality data from laser diffraction. The range of organic content suggests pre-treatment may be advantageous. Like I said, that's a pretty wide range. And furthermore, the difference in the densities of the 2 materials, meaning density of organic content and the density of mineral soil, kind of suggests that probably could be investigated further. As far as the mineralogy is concerned, basically the findings confirmed our refractive index, which is a setting in the laser diffraction machine. Refractive index was 1.544. That was an assumption of the mineralogy, largely, quartz. It just confirmed what we had assumed going in. So yeah, hypothesis 1, the mean values for a racing surface can be characterized with 8 samples. That's particularly useful for selecting top dressing material and divot mix. So that way, if you select top dressing and divot mix material that matches the mean value, you should be minimizing variation as you go along, and you should be preventing layering and drainage issues that could occur if you select incorrect material. We do not think that the variation is accurately represented by 8 samples. I mean, rarely would you ever actually collect 96 or more samples to fully capture all of the variation, but it's useful to know that this is kind of the limitation of the method. Hypothesis 2, native soil tracks are, like I said, native soil with no or minimal modifications. Engineered surface without fiber, again, so they retain some fine content to increase shear strength, and engineered with fiber uses synthetic fibers to increase shear strength and not inhibit drainage. So laser diffraction was able to detect differences between racing surfaces. This was using samples as small as a 1/4 gram. So we were able to detect differences between racetracks with small samples and get a faster turnaround time for racetracks. This allows us to produce a minimal disturbance of the racing surface and we can accurately characterize the mean values of a racetrack in as few as 8 samples. Like I said, though, there is a need to further discuss handling of organic content. All right, I'm going to do a quick time check. All right, race day measurements. This was our second paper. As I said before, the OBST is the primary method for assessing a racing surface. It's the subject of an ASTM standard on that exact topic. It is ideal for assessing the surface prior to a race meet, but it does have limitations for daily use. Daily measurements are required by HISA. And that then begs the question, okay, so what data do we take? What is feasible, and what has some kind of correlation to biomechanically based measurements? There are many different tools out on the market that have been used in turf applications. They are simpler than the OBST, they're more cost effective, and they produce less surface disruption, but they have not been evaluated for use in equine. Well, many of these have not been evaluated for use in equine applications, and none of them have been put sort of head to head against the OBST to say, what could these basically, could any of these tools approximate the findings of an OBST? So the purpose of this study was to identify simple tools that are suitable for daily use at racetracks and can provide quantitative data to describe the condition of turfgrass racing surfaces on race days. And obviously, tying back into the first paper, we had to consider the range of surface compositions that we encountered in North American racing. As luck would have it, Michigan State University's Hancock Turfgrass Research Center had a test plot of 15 different soil compositions. Those had different, so like I said, 2 sand profiles, 4 different sand, silt, and clay mixtures, 2 soils with natural reinforcing materials, and 7 soils with synthetic fiber reinforcement. So a pretty good mixture that closely mimics what we found in North American turf racing. Compositions are comparable to what we found in the laser diffraction paper. So data was collected with each of the tools mentioned at 3 different moisture levels: an OBST, which measures cushioning, impact firmness, grip, and responsiveness; the moisture probe, which of course measures volumetric moisture content. We used a 2.25 kilogram Clegg hammer. We did that, so we did 3 drops of the hammer without moving the tube. That allowed us to report the data 2 different ways. The first of which was only reporting the first drop, which is consistent with ASTM F1702. That's a general playing field surface ASTM standard. And then the average of the second and third drop is based on ASTM F1936. That is actually for North American football. We also used a Longchamp penetrometer. We took a penetrometer reading prior to and after releasing the 1 kilogram mass. So we reported that data both ways, meaning the delta between those 2 measurements and just the maximum penetration. We also used a turf shear tester that only reports shear, and a going stick, which reports penetration, shear, and going index. All of that data was put into SAS. We looked at correlation coefficients, and we produced many different linear models for each of the variables in question to see how they may or may not be able to approximate the 4 parameters measured by the OBST. The goal of which was to identify the simpler tools that could allow us to approximate the parameters measured by the OBST and identify the tools that should be used on race days. There were 404 total measurements with each device. There was 1 erroneous OBST drop that was discarded, along with a corresponding measurement from the other tools as well. The moisture probe had the strongest correlation to cushioning, impact firmness, and grip. Moisture probe pretty quickly rose to the top of the pile when you started looking at the data. The Clegg, if you only look at the numbers, the correlations and the linear models, and just follow the numbers, the Clegg impact hammer was the second strongest correlation to all 4 OBST parameters. The average of the second and third drops, so that was the one that was based on North American football, that was better suited to the OBST than the first drop, and that's true across the board. Longchamp penetrometer was also neck and neck with the Clegg impact hammer, and the delta of the 2 measurements before and after dropping the mass was better suited to the OBST than the maximum. That was also true across the board. The Turf Shear tester had high correlations to responsiveness and was included in a 3-tool linear model. I'll show, well, actually, that's in the backup slide, sorry. I can show if there are questions, but there was a 3-tool linear model that just said, if you follow the numbers and only pay attention to the numbers, this is what you would do. The Turf Shear tester was included in that because only looking at R² values, it was able to approximate responsiveness reasonably well. So like I said in the beginning, the moisture probe very quickly rose to the top of the pile. The going stick pretty quickly rose to the bottom, or fell to the bottom of the pile. It had the lowest correlations and contributions to linear models across the board. So now we get into discussion mode where we're looking at more than just the numbers. So like I said, so for the OBST, cushioning and impact firmness were pretty well characterized by the simpler tools. Grip and responsiveness were pretty difficult to capture. A lot of that can be attributed due to the noise in the measurements. The OBST remains the primary device for assessing grip and responsiveness. That's essentially the punchline that we walked away as far as that goes. Moisture probe, again, strong correlations and contributions to linear models across all OBST parameters. There's established links in the literature between moisture content and peak load on the hoof. Moisture probe is also the primary measurement conducted in Japanese racing, and it's regularly collected in North American racing. It provides little to no surface disruption. It's super easy. You stick the moisture probe into the ground and you push a button and there you go. Moisture probe is the no-brainer. Clegg impact hammer, like I said, very strong correlations. Average of the second and third drops was better across the board. There were some concerns over the ability to characterize day-to-day variations with a lightweight projectile. Obviously, it's a 2.25 kilogram mass that's dropped from, I think, 0.47 meters, if I remember right. You can imagine that there are concerns over whether or not that could accurately represent the hoof of a horse running at 40 miles an hour. Yeah, particularly when you factor into the equation that turf is strain rate dependent, right? Longchamp penetrometer, the big finger on the scale for the Longchamp penetrometer is that there's an established link in literature between race times and injuries in New Zealand. So, and that's also on turf. I need to point that out as well. So that quickly moved the Longchamp penetrometer above the Clegg impact hammer for that reason. We know from reading that literature on New Zealand racing, which is again on turf, that penetrometer measurements have a direct link between performance and injuries. Turf Shear tester, like I said, was a strong result with responsiveness, but the R² for responsiveness never really gets above 0.07. So that's not moving the scales enough to really warrant inclusion into daily measurements. The going stick had several issues. 53 of the 404 measurements were collected at the upper limit of the tool. So basically what we're thinking is it's probably not the right tool for assessing North American surfaces. That was developed in the UK. It appears that North American surfaces are quite different from those encountered in the UK. That might be part of what's going on here. But like I said earlier, it's difficult to measure consistently. It's not a falling mass drop from a fixed height like the Clegg hammer or the penetrometer. And turf is strain rate dependent. So fixed energy input is a big reason why the Clegg hammer and the penetrometer gave better results. So the conclusion there was volumetric moisture content, like I said, is the no-brainer. I mean, collect that every day. There is, I mean, direct links to biomechanically based measurements, links in the literature to load on the hoof. It's kind of staring you right in the face. Longchamp penetrometer, the delta between prior to this is me right here with a Longchamp penetrometer. So the delta between the measurement prior to and after dropping the mass is preferred over the Clegg hammer, which is on the far right here. The average of the second and third drops due to established links between both horse performance and injuries. The turf shear tester and the going stick were not overly well suited to representing OBST data. And again, the OBST, which is here on the far left, is the primary device to assess grip and responsiveness. So that doesn't change. All right, last research paper. So we know the ability to continue to race on turf during or directly following inclement weather is very important for turf racing. There's, you know, turf starts have increased significantly over the last decade or so, and so we need to be able to hold as many races on the turf without moving them to the adjacent dirt or synthetic track as much as we can. So in order to do that, we need free draining profiles that can support a thoroughbred at a gallop. There is decades of research in golf and other athletic fields application. Basically, we're wondering, is this a solved problem? Obviously, those applications do not have the same considerations for a 1,000-pound animal running at 40 miles an hour. We know that fiber reinforced high sand content surfaces are common in North American racing. We also know that we can assess them for HISA. Are they advantageous, and how so? In a quantitative fashion, can we characterize that? Natural fibers are also a really interesting solution to some issues seen with synthetic fibers. By that I mean there are environmental issues with generation of microplastics in situ, and we also know that synthetic fiber reinforced surfaces do increase surface hardness over time as they receive traffic. So we wanted to look at natural fibers as well and see if there was potential there to do a lot of the same things that synthetic fibers can do for us. So to test this, we collected soil from a golf course here locally in Lexington that meets the USGA recommended profile. We evaluated that soil without fiber, and then with synthetic fiber reinforcement and jute and sisal fiber reinforcement using a ASTM triaxial shear method, and discuss potential advantages and disadvantages in a turf thoroughbred racing application. We did perform laser diffraction and organic content on this material, identical to the first paper. We also performed the laboratory compaction procedure, as we were talking about with Lexi's research, to find the forming moisture content that produces the peak bulk density. We then conducted triaxial shear at that forming moisture content on the material with no fiber. Then to that same golf course soil, we added polypropylene fibers at a rate of 4 grams of fiber per liter of soil, and did triaxial shear at a range of moisture content surrounding that forming moisture content above. We expected the forming moisture content to change slightly with the addition of fiber, but we wanted to look at a range of moisture contents to see pardon me, how this may or may not change, how the shear strength may or may not change with moisture. And then we did the same thing with natural fibers, jute and sisal. They're made from reclaimed coffee bags, for the record. So those large bags of coffee beans in your local roaster shop or whatever, those are shredded to and reclaimed in this effort. So we applied the natural fibers at the same rate, 4 grams of fiber per liter of soil, and then did triaxial shear at the same moisture contents that we did with the synthetic fibers. All triaxial shear was conducted at 5, 10, 15, and 20 psi confining pressures as defined in the ASTM standard, and it was also just at ambient temperature. Laser diffraction found that the soil would have firmly been placed in the engineered with fiber archetype. That's pretty useful for the comparison that we're about to do here. I've got full details of everything if we want to look at it. Organic content was 3.5% by mass. Soil without fiber, the forming moisture content was found to be 17.4%. The friction angle was about 29 degrees, and the cohesion about 3.5 psi. When you add synthetic fiber, so we did triaxial shear at 16, 17, and 18% moisture content. Again, kind of trying to bracket this forming moisture content of the material without fiber. So the friction angle changed from 29.4 degrees to 31, 33, and 31 degrees at those different moisture contents. And cohesion went down pretty significantly from 3.5 to about 1.5, 1.6, 1.8 psi. When you look at natural fiber, again, the same sort of setup here, 16, 17, and 18% moisture content. Friction angle without fiber was 29. That went to about 32 to 33 degrees. And cohesion, 1.4, 2.58, 1.4 psi. So those difference, what we found is that synthetic fiber increases friction angle by about 10%. So that's what is friction angle? It's the rate of increase in shear strength. This is sort of the governing equation relationship to sort of discuss the results around here. The Mohr-Coulomb relation, where tau is the shear strength of soil, is equal to the normal stress applied and the tangent of the friction angle plus cohesion. So it's basically y equals mx plus b. So the friction angle here is the rate of increase in shear strength. Any opportunity you get to increase friction angle is obviously for the better. The surface is less likely to fail in shear, which is critical for supporting the horse. Addition of synthetic fiber decreased cohesion by almost half. So cohesion, what is that? That's essentially how tightly soil particles are bound together or held together. This is advantageous for thoroughbred racing because the kickback created by divots will be in smaller pieces. So should the surface fail in shear, which ideally wouldn't happen, that would be, smaller pieces will be thrown at the jockeys and horses behind them. The addition of natural fiber produced comparable increases in friction angle and decreases in cohesion. You might have noticed from that slide previously, there may have been a unique relationship with moisture content, although that could be influenced by the fact that we had to prepare a unique batch for each moisture content with natural fiber. We dry material at 60 degrees C, which is pretty darn low actually, but that's actually quite close to like the flash point of jute and sisal fiber. So we did not put those materials in the oven because we were concerned about potentially degrading those materials. So there may be minor variations in preparing a new batch. But natural fibers are really a promising alternative to synthetic fibers. because we can get a lot of the same performance benefits that we see in synthetic fibers, but we wouldn't have the issues with environmental issues with microplastics, and natural fibers would of course biodegrade over time. So that makes them really well suited for divot mix applications. Most soils in the engineered with fiber archetype will not have fibers in their divot mix. So you see they could be adding soil with about a 29-degree friction angle to a material that has about a 32 to 33-degree friction angle. So the ability to include natural fiber would allow us to increase the shear strength of the divot mix to better match the existing profile while the turf grass is actually taking root. So it's could be a really unique solution in that sense. And it's also could potentially be an alternative to synthetic when you look at the increase in surface hardness that synthetic fibers show. Yeah, like I said, so synthetic fiber, substantial increase in friction angle and reduction in cohesion, both of which are advantageous for thoroughbred racing. Natural fiber produces comparable effects on both friction angle and cohesion, with the added benefit of environmentally conscious and biodegradable fibers. I know I'm a little bit over time, so I'm trying to wrap it up quickly. So what we found, laser diffraction is an important tool for determining the particle size distribution of the racetrack. We can characterize a racetrack in as few as 8 samples that are as small as a 1/4 gram. Moisture content and penetrometer readings should be collected on turf surfaces daily. So that helps HISA tremendously and helps racetracks superintendents as well. We also found that natural fibers have a comparable increase in shear angle of racing surfaces to that of synthetic fibers. This allows for decisions regarding the construction of new tracks and the maintenance of existing tracks to be data-driven, as opposed to, qualitative. Everything is, we've done our best due diligence here to make as much of it quantitative as we possibly can. And then we can take data from this work to be added to epidemiological models, in particular the first and second papers, but really all of it. This would help us understand how the surface can affect both performance and risk of injury. The recommendations for future work, like I said, I think we need to probably, it's worth a deeper dive into organic material for laser diffraction. For the second paper, it's pretty easy, right? You implement the daily surface monitoring protocol, and hopefully in time, after we've collected enough data, we compare those measurements with race times and injuries and start to learn something from that. And then for the third paper, the recommendation is to investigate how long those natural fibers last in the soil profile. That'll be greatly dependent on climate and a lot of other factors, and potential effects on surface hardness with traffic and age. All right, so we're at the end here. Just wanted to say thanks, obviously, to the Central Appalachian Regional Education and Research Center. They've provided a lot of financial support for this research, and it's greatly appreciated. Also wanted to recognize my graduate committee, our cohorts at Michigan State University who partnered with us on that second research paper, and the folks in the room there at RSTL. And I'll stop for questions.